Good morning. So, today we will talk about the challenges that we have with the CO2 chiller, uh, more on the design side. And I'm just considering one particular scenario that if there is a power failure or if the chiller has to go in standby for, let's say, couple of days, then what are the things that needs to be taken care of in design context. So, like, what is the difference between like, let's say there is a normal freon or a typical ammonia chiller, compared to that, if there is a power failure, what is something different that we have to do while designing the CO2 chiller? So, so this video will be more around that. And I'm just considering only one challenge. Uh, in future, I'll, start addressing like the other challenges. But one of the challenges that we are going to talk about is if there is a power failure or the chiller has to go in standby for a long period of time, what considerations, design consideration we should consider in the refrigerant circuit. So let's jump into it. This is more of the overall CO2 refrigeration cycle. I'll just walk through this. This is the evaporator where we are looking for lower temperature, like in the freezer or in the process. It's a typical evaporator that we have in our refrigeration cycle with the Freon. It's identical to that. And the job of this evaporator, LT evaporator, is to convert the liquid into the gas so that it can be sent into the LT compressor. LT is a low temperature compressor. Here the pressure goes up and it goes into the medium temperature compressor. This is where the pressure is goes up. It goes into that transcritical state. Uh, I'm not going to touch on that, but I'll just say that uh, the temperature goes up and the pressure goes up and it goes into the gas cooler, which is different than the condenser, which we would typically have over here. Gas cooler, because it's in the gas, the CO2 gas is in a transcritical state, goes through the expansion valve, and out of the expansion valve, it will be a liquid and a gas. The liquid will be just accumulating in the bottom of the flash gas tank, going into the expansion valve, going into the LT evaporator, whereas the flash gas will be going back into the medium temperature compressor. I'll just put some numbers to this circuit so as to make little more realistic scenario. So this is my current uh, project that I'm working on, and the evaporator, it is I need the process temperature, or let's just say the refrigerant temperature to be at negative 22 degrees Fahrenheit. It converts it into gas, goes through the LT compressor. The pressure is raised to like 624 psi, and its saturation temperature is 46 degrees Fahrenheit. This might be superheated over here, the gas, uh, we can we so we will have to add like a desuperator before it enters into the empty compressor, and outlet of the empty compressor then goes to the gas cooler. Uh, Currently, I have considered 80 degrees Fahrenheit as my ambient temperature, and I have considered a delta T between the ambient and the outlet dry gas cooler temperature as uh, almost like 8 degrees Fahrenheit, or let's just say 4 degrees C, 4 Kelvin. So it is about 1 1105 psia coming into the expansion valve and then coming into the flash gas tank receiver, which is a bit higher than the whatever is the suction of the empty compressor. So so now, like, this circuit is running, we are getting uh, you know it's running in the condition that it is giving 22 negative 22 degrees Fahrenheit of the evaporation temperature. Now let's say we want to shut the cooler down, shut the chiller down, because we don't need this heat or cooling, or the process is not running, or for whatever reason we put into this chiller into a standby condition. What happens? Now, when we will put this chiller into the standby condition, let's just say the the pressure is completely killed in the entire circuit. That means that all the entire circuit is not having any driving force per se. So this this is already, so when I say the temperature will be there 80 degrees Fahrenheit, the this compressor is killed, so the outlet pressure would be like, let's just say, uh, you know I think on the suction of this at negative 22 degrees Fahrenheit, the pressure is about 196 psia. So, so this will be 196 psia. So now imagine this compressor is off. This compressor is off. The This side of the refrigerant on the low temperature side is negative 22 degrees Fahrenheit, and it is at 196 psia. But this side of the refrigerant earlier was at 640 psia and 48 degrees Fahrenheit. So, and this is the hot side, which was at 88 degrees Fahrenheit. But let's just say the accumulated temperature and the pressure was more around 640 psia, so 48 degrees Fahrenheit. And let's say this, since this is the accumulated, let's just say even this gets heated up easily to 48 degrees Fahrenheit now. So the pressure will keep on rising to like 640 psia. Now what happens? Now, because of the insulation losses, like since the ambient temperature is 80 degrees Fahrenheit, the ambient temperature, due to the insulation losses, will try to put the heat into this flash gas tank receiver. And as the temperature will rise, the pressure will keep on rising up. So, so if we want, so this is what we want to say here is that what happens when the CO2 chiller is in standby condition. So there is an increase in the pressure. We call it as a high standstill pressure risk, which means that there will be increase in pressure. The flash tank gas temperature will keep on rising, and hence the saturation pressure will keep on rising due to the insulation losses. So now let's just see like the properties of CO2. So we know that at 80 degrees Fahrenheit, let's say in between this 75 and 80, so we know the pressure is going to go up to like 1000, in between, let's say 900 and 1000 psi. So the pressure will keep on rising. And let's say uh, we have a very hot day and the pressure goes up to like, sorry, the temperature goes up to 105 degrees Fahrenheit, which will be like almost 1500 psia or 1468 psia. So in that case, what will happen? Uh, let's say, let's take this case that the ambient temperature is 110 degrees Fahrenheit. Now, and let's say this flash gas tank receiver temperature also comes in equilibrium. And now the pressure would be almost like 1468. So 1468 psia. This this relief valve will pop up and open. Now, one of the very important thing to consider is that on this flash gas tank receiver, there should be a relief valve for conditions like this, where the ambient temperature is high and the pressure does go up to, you know, more than 1300 psi. So for this condition, we have a relief valve. But if this relief valve pops open, we will release the CO2 gas into the atmosphere. And when we are ready to start again, we might have to fill it up again with this CO2 gas. So, what do we do in the design to eliminate this condition of refilling the CO2 gas into the refrigerant circuit? What we do is we give a something what we call as a standstill cooling unit, or let's say cooling coils. Uh, what we have is inside the flash tank, flash gas tank, we have refrigerant coils, which then reduces the. So the way it works is there will be a pressure transmitter. As the pressure goes up to, let's just say, if the pressure goes beyond 1000 psi, the standby or standstill cooling unit will fire up. It will send the cold refrigerant in and cool the vapors that have formed inside the flash gas tank receiver such that these vapors will then condense, go back into liquid, go back into the solution or convert it into CO2 liquid and hence reduce the pressure to, let's just say, 900 psi. So, and then once it reaches 900 psi, the standby cooling unit stops and the pressure is maintained and monitored. uh, Again, if the pressure goes up for some reason, let's say the chiller is still in standby, then the it hits 1000 psi. uh, the stand still cooling unit starts and it starts condensing all the vapors, CO2 vapors, into liquid and stops when the pressure reaches 900 psi. I'm just giving one as a reference point, just for a reference. The actual set point pressure might change, but this is just as a reference. So this is applicable when chiller has power and it is in standby. This is not applicable when there is power failure or a power outage. In that case, relief valve is the only way we can maintain the pressure inside the flash gas tank. And in that case, we will have to top it up with some CO2 when we are starting up the system again. So, so these were the two important constraints to keep in mind when designing the CO2 chiller, which is different than the freon or ammonia system, that ammonia chiller, that we have to give something called a standstill cooling unit for standby conditions for a longer period of time, and a relief valve for the power failure or the uh, power outage condition. So, thank you.